Hey everyone, so here's our third lesson in our Earth and Climate Change unit, and we're going to be focusing on Earth's atmosphere. So you've heard that term before, I'm sure. The atmosphere is just a blanket of air and moisture, which is really just water vapor, that surrounds our planet. It is important to help life grow. It helps keep our weather systems relatively constant. When you think about the atmosphere, you just kind of think of the air above us perhaps, or the ozone layer, but it is a little bit more than that. Um, the atmosphere does start just at sea level and extends about 500 kilometers straight up, at which point we get into the vacuum of space. So the atmosphere is quite large. It's broken up into different sections, which we'll talk about, but we're first going to start talking about air and the chemical makeup of air, which makes up our atmosphere. It's a little bit of a misnomer that the majority of the air we breathe is oxygen, which some of you may have heard before. Hopefully, you know that that's not true. The majority of the air we breathe in is actually nitrogen, close to 80%. Depending on the source you read, you might see it written as 80, 79, and 78. It just depends on how they round. But this chart's showing you that nitrogen makes up about 78% of our atmosphere, for the air we breathe, sorry, and oxygen only makes up about 21%. So just over a fifth of the air that we breathe is oxygen. And of course, we know that we use oxygen to power our muscles. It's transported throughout our body via our circulatory system and our lungs. Also made up, or also present in air, are a couple of other gases that you may not have thought of. Argon makes up just shy of 1% of the gases in air. Carbon dioxide, which we're going to talk a little bit more about on the next slide, makes up, now it's closer to 0.04% now, and we're going to talk about that a little bit later. This is a little bit of an older chart. The remaining, if you're doing the math here, you'll know that there's a little bit left over. That little remainder, whatever that percentage might be, is made up of a couple of inert gases, helium, there's neon in there, and then things like methane and, of course, ozone. The composition of air, the chemical makeup of our atmosphere, does change depending on where you are on the planet. The closer you are to the surface of the Earth, the closer you are to sea level, you might get a little bit more water vapor in your atmosphere. And if you're in a highly polluted area, you might get a little bit more SO2 or sulfur dioxide. So if we talk about carbon dioxide a little bit, it's present in trace amounts, so it's not very much compared to, say, oxygen, nitrogen, or even argon, but it plays a very big role in the functioning of our planet. Carbon dioxide is, of course, a greenhouse gas. You've heard that term before. A greenhouse gas is just a gas that is effective at absorbing and emitting radiation as heat. Carbon dioxide is the kind of the big one, the big hot topic nowadays. If you take a look at the website co2.earth, it gives you scientific data on the levels of carbon dioxide in our atmosphere. The last set of data I believe that is published is from November of 2016, so just maybe a month and a half, 2 months ago. And it's telling us that the current concentration of carbon dioxide in our air in the atmosphere is 0.0403%, also listed as 403 parts per million. So you should be able to make that conversion between percentage and parts per million. Why is that important? Well, if we take a look back pre-industrial revolution, the CO2 levels on our planet were about 275 ppm. Post-industrial revolution, that number has gone up steadily, especially in industrialized nations. You look at China, you look at the United States, Canada, of course, a lot of Western countries. Countries in Europe are contributing a lot to the levels of carbon dioxide in our atmosphere. When we take a look at a couple videos in class, we'll see how that's compared around the world. The safe limit for CO2 in the atmosphere was considered to be around 350 parts per million. We've recently hit 400, which is what is kind of being thought of as a threshold of no return. Right? We're never going to be able to recover from this. We've hit 400 ppm, and we're never going to really be able to recover, bring the concentration in the atmosphere back down to a place where we're not contributing to global climate change, and where humans aren't having this profoundly negative effect on the environment. I would like you to check out this article written in Scientific American. Earth's CO2 passes the 400 ppm threshold. It gives a good account as to what that really means. So let's go back to the atmosphere. We're going to focus more on greenhouse gases and their effect on the environment in our next lesson. But right now we talk about the importance of the atmosphere. There is a natural greenhouse effect, which is good. This is what we want. The problem is now that we have contributed too much to this greenhouse effect, and it's causing problems. So this natural greenhouse effect helps us control temperature extremes. It helps keep Earth's surface warm enough for us to survive and warm enough for plants and animals to thrive. It reduces these huge extremes in temperature that could be possible between the middle of the day and the middle of the night if that heat was not trapped, right? If all the heat left the planet right away, it would be incredibly cold at night. Maybe in some areas so cold that we wouldn't be able to survive. The atmosphere is made up of an ozone layer. Ozone is O3, so it's 3 oxygen molecules bound together. This is a very high energy, very strong bond. Ozone is able to protect us from ultraviolet radiation, does not let as much of the UV radiation from the sun pass into the earth as is available, so that's good for us. When you put on sunscreen, for example, it probably says UV protection on it, or UVA or UVB, so that helps protect us against skin cancer. Some of the other elements, or some of the other compounds and molecules present in the atmosphere: O2, CO2, H2O, so oxygen gas, carbon dioxide gas, and water vapor. All of these are necessary for survival, right? We know that oxygen is needed for animals and plants to survive. Oxygen is needed for humans and animals to survive. Carbon dioxide for plants. Water, we all drink water. It's also a necessary component of the water cycle, right? So our atmosphere has these convection cells. This is the way that gases and then heat and energy are kind of moved throughout the atmosphere. So these convection cells, they force warm air and moist air to rise at the equator. They also force cool and dry air to sink down at the poles. They cause energy, or heat energy and moisture, to be transferred around the globe to the poles as well. So these are what we're going to call convection cells. Lastly, when we talk about the atmosphere, we talk about the layers of the atmosphere. Now, depending on where you are, these numbers change a little bit. Depending on the source you get, you might see, for example, the troposphere is 10 kilometers, it might be 20 kilometers. But if we start at the troposphere, generally 0 to 20 kilometers above sea level. All of these values are above sea level. An example here is at the north and southern poles. It's approximately 8 kilometers. This is where we live, right? This is where our weather takes place. Most of the atmosphere's moisture is located here. Next up from that is the stratosphere. So this is our ozone layer, 20 to 50 kilometers. This is kind of where planes fly. Again, that number does change depending on whether it's a commercial aircraft or a military aircraft, maybe a weather balloon, or they have all kind of got their different altitudes that they fly at. The mesosphere, meso being meaning middle, is the middle atmospheric layer, 50 to 85 kilometers above sea level. At this spot, if a meteor, for example, is coming in from space, it is in this range where they typically burn up, and they actually don't typically make it down to Earth. The thermosphere Here's a larger range, 85 to 5 to 600 some odd kilometers from sea level. Gases are ionized up here. So this is, for example, where the aurora borealis or the northern lights take place. That's just ionized gases. This is the orbiting area for space shuttles as well. And then the exosphere, over 500-600 kilometers from sea level. This is where we get satellites to orbit. This red line, this kind of red curve that we see on this graph, is our temperature curve. So in the troposphere, we have these temperatures, let's say an average of about 15 degrees Celsius. As we leave the troposphere, head into the stratosphere, we're, ranging between -50 to 0 degrees Celsius. In the mesosphere, we can go as low as -100 degrees Celsius. The thermosphere, depending on where you are, there's a large temperature range. You can see at about the 110 kilometer above sea level area, that temperature shoots right up, and then we get up into our exosphere. And then, of course, after that we're leaving our Earth's atmosphere altogether. We get into space where we're very, very cold. We're in the vacuum of space. So that's it for this lesson on the atmosphere. Hopefully you were able to fill out all the notes. You can leave any comments below, or you can ask me some questions when we're back in class.